record on this computer. So I received 14 responses about when you want the final exam. 5 people said they want to keep it on the final exam day of May 1st. 7 people said that they would like to have it on Friday, April 23rd, and 2 people said that they would like to have it on Monday, April 26th. So as of right now, it looks like maybe we should do May 1st and April 23rd as like 2 exam days. I don't think that I can swing 3 exam days just like based on fairness and how much I have going on and everything. So as of right now, I'm thinking about doing Friday, April 23rd. Yeah, Kaya, I saw yours. I counted it. Friday, April 23rd. And then the exam day of May 1st will be our 2 final days. And you can pick which one that you would like to do. If you can't make either of these days, I think you have to, but just let me know if you have anything that is outstanding and you really have to take it on another day or something. I'm trying to be flexible because I know that everything is, I don't know, the world's insane right now. So I think we're going to have it on Friday the 23rd and then a slightly altered but similar exam on the 5th. So there will be, you can pick which final exam that you want. You don't really have to let me know beforehand which one you choose. You can just come, but only come to one. Don't take it twice to see if you do better on one. Just come to one. And I will be doing a review for both groups of whichever one you decide next Wednesday. So if you don't want to take the exam on the 23rd, then just use that time to study and then come on May 1st. And if you want to take it on the 23rd, you'll have an exam you'll have a review on Wednesday and then the exam on Friday, and then you'll be done with the class. So any questions about that? Sorry if that's a little confusing, but you can either take the exam Friday the 23rd. Yeah, say that again. Abed, were you asking a question?
Am I done with the exam yet?
Oh, yeah, unfortunately, no. I know it feels like we should be. There's only one more. And if you want to go ahead and get a jump start on studying, the exam will have a question on Gibbs free energy because you haven't been assessed on that yet. And then it will mostly focus on chapters 4 and chapter 5. And chapters 4 and chapter 5 are the ones that we were looking at with like steady flow systems, our property tables. So chapter 4, chapter 5, and a Gibbs free energy problem. And then you're going to have about, right now I have 7, but I think it's going to be 10 short conceptual questions. They're going to be very short and quick, like what is the gravity, what are units of gravity? Something that you should just kind of answer. Some of them will come from your memorized sheet, some of them will be just like conceptual questions, like, an exothermic reaction has a delta H of, and you should say like negative or positive, right? Like they should be really quick conceptual questions. And then there will be longer questions. Gibbs free energy, chapter 4 and chapter 5 are the main focus. So there's only one memorized sheet. It's the one that was posted like at the first day of class. So there's only that one like memorized sheet. That there's 1,000 joules in a kilojoule, that, joule per second is a watt. Yeah. So just that first memorized sheet. And yeah, so Gibbs free energy, chapter 4, chapter 5, some conceptual questions. It should take you about the same time as a regular exam. No, there's no cheat sheets allowed again. You shouldn't really need them. The final is, to me, I made it just like I would make a normal exam, except for I added a few more conceptual questions, and that's about it. Yeah. I used to allow cheat sheets, but I changed the way I'm testing the exam. When I allow cheat sheets, I make the exam harder, and I actually had like lower averages because I like to ask questions that are very similar, if not the same, as ones that I've assigned for homework or done in class or done whatever. And when you have a cheat sheet, you can't do that. So the exam becomes harder. So that's why I don't allow cheat sheets. But other questions? Okay, so I'll send an email to the class that will have the 2 exam options. That means that a week from today will be like the last day of like class. That's not exam. So we're really close. Today, I will be presenting some new material, doing some example problems. Class is canceled on Friday. And I am giving a talk about my career path for my former program at Duke. So class is canceled on Friday, in case you missed that on Monday. And then Monday we'll have new material. Wednesday is review. Friday is the first option for the exam. So we are so close. Keep your head up. You're almost done. Summer is right around the corner. If you dress up like Beefy, could there be extra credit? So it's going to be very tricky to dress like Beefy and not be offensive, because Beefy is chubby. He got big old jowls. He is the cutest dog in the whole world, but yeah, muscular. he's not muscular. I don't know. Let me think about it. Ask me again on Monday. Maybe. I mean, I think it would make me laugh. So is that worth extra credit? Probably. Yeah, that could be a good option. I was thinking about putting a question about Beefy on the exam, like who is the best dog in the world, but I didn't want to offend other dog owners. So we'll see. Okay, so other questions? I know. So it would have to be like, you know, yeah, I don't know. It's hard. Like who's my best friend and the best dog that lives in my household? You know? Yeah. Okay. Who do you hear snoring in 85% of the videos that I've posted this year? No. Okay. So any questions before I start going over Gibbs free energy more? All right, great. So, yikes. We're going to be continuing with Gibbs free energy. I looked up some stuff after Monday's class about how balancing equation like affects KEQ, because I know there was like some confusion about that on my part. So I looked it up, and I have some good examples that demonstrate this concept. So if we have an example problem that has, we are given this equation, 1/2 a mole of I2 gas, iodine gas, plus 1/2 a mole of chlorine 2 gas can become iodine chloride, iodine chloride. I don't know. I think this is what's like in some salts, but it doesn't matter. And then you're given the KEQ is 4.54 times 10 to the 2 at 25 degrees Celsius or ambient temperature. So what I've decided is on an exam, if I'm giving you a KEQ value associated with the equation, I will give you a balanced equation, because there are some rules about this. So if you want to have this equation actually be 2 I2 gas plus 2 chlorine gas can create 4 ICl gas, then you need to raise your KEQ to the 4th power. So I multiplied this entire equation by 4. So I needed to raise my KEQ by that same power of my multiplier. I need to raise it to the power of that multiplier. So KEQ to the 4th, or 5.54 times 10 to the 2 to the 4th power, which actually becomes 4.25 times 10 to the 10 for this equation. My KEQ is much higher. And this makes sense because KEQ is our product, our concentration of our products raised to the stoichiometric powers divided by the concentration of our reactants raised to their stoichiometric powers. So if we are multiplying these powers, our molar amounts, by a certain factor, then that needs to be reflected in the KEQ by bringing it to that same power. So on an exam, I will give you KEQ with the balanced equation that it is associated with. Okay. Conversely, if we had an example problem where we had 2 I2 gas, so starting this equation again, 2 I2 gas plus 2 Cl2 gas can create 4 ICl gas, and our KEQ here was 4.25 times 10 to the 10. If we wanted to make this equation a lower multiple, so I2 gas plus Cl2 gas goes to 2 ICl gas. In order for us to do this, we would need to logically take the root to our factor that we divided by of the KEQ. So this one is the square root of 2 of our KEQ value, because we divided our whole equation by 2. Here we multiplied by 4, you have to take it to the power of 4. We divided by 2, you have to take that square root to that of that power. So if we divided by 3, it would be the cubed root, which mathematically that should be very comfortable, right? That makes total sense. But so the KEQ of this equation becomes 2.06 times 10 to the 5. All right. So there's another thing that I told you on Monday that I'm going to ask you to practice now. Given this example, what is the value of the equilibrium constant for the following? We have 2 NO2 gas that can create 2 N2O4 gas with a KEQ of 4.72 at 100 degrees Celsius. So I should have worded this better, but find KEQ of the reverse reaction. Find KEQ of the reverse reaction. So I'll give you a couple minutes to do that. Type it in the chat when you have it, but find KEQ of the reverse reaction. Yes, Noah. Yeah, that looks good. Okay, so it seems like several people have gotten it. So remember on Monday, I told you that if you reverse a reaction, you need to take the inverse of the KEQ. So if we're finding our KEQ prime of the reverse reaction, so KEQ of reverse reaction, this is going to be equal to a 1 over our original KEQ, or 1 over 4.72, which gives us about 0.212. This is our new KEQ for our reverse reaction. I just denoted it with a prime symbol here. So that's another little KEQ trick that we have. All right. Here's another problem that we're gonna do. So we have this example problem where we want to calculate KEQ for the following. We have 2 grams or 2 moles of nitrous oxide in O gas plus bromium gas, which goes to 2NO(Br) gas. And we are given the following. 2NO gas can produce nitrogen gas plus oxygen gas with a KEQ of this first equation, KEQ1 of 1 times 10 to the 30th. So a huge KEQ, huge. And then we have a second equation where we have nitrogen gas plus bromium gas plus oxygen gas can create our 2NO(Br) with a KEQ2 of 2 times 10 to the minus 27. So using the chat, is this KEQ product favored, reactant favored, or about equal? Yeah, Emma, Noah, yeah, it's product favored, right? This is a huge value. Values over, I think we said a KEQ of 1,000 are pretty much exclusively all products. And below 0.001 was pretty much exclusively all reactants. So this KEQ is almost entirely all reactants. And this KEQ is saying that this equation is almost entirely all products. So when we, similar to enthalpy, when we are looking for KEQ of one equation and we're given KEQ of these equations of formation that can make this overall equation. We need to figure out if we need to, how we can combine these to make our resulting overall equation. So this one is easy because I don't need to reverse anything. I don't need to multiply anything by anything. I can just kind of add these together. So my nitrogen gases are going to cancel, and my oxygen gases are going to cancel. These are on two separate sides of the equation. I'm sorry I wrote the equals so far away. And then I'm going to be left with the 2NO gas plus Br2 gas creates, that's a bad creates 2NOBr as my resulting equation, which is my overall starting equation. So that's great. And in order to find the KEQ here, unlike enthalpy, I cannot add, I need to multiply. So our KEQs here get multiplied. I have 1 times 10 to the 30 times 2 times 10 to the negative 27, which gives me a KEQ of 2 times 10 to the third. So this is still product favored. This reaction is still product favored. But the lesson here is that KEQs are multiplied when combining equations.
Question.
Is that always the case? Like, are there any weird, like, I don't know, reactions that you'd have to change that for any reason?
So I mean, as I went over before, if you reverse this equation, you need to do the inverse. And if you have to multiply an equation by something, you need to take it to that power. But otherwise, when you're combining equations at the end, they will always be multiplied together from what I can think of right now. If there are some weird anomalies, I'm not going to be assessing those. So those won't be on an exam.
Okay, thank you.
Yeah. What was the other questions?
I think that was my question too. I can't remember from, it's been a while since chemistry and what we've been doing in this course, but so like if we have givens and let's say if we had to multiply like 2, for example, like the given equation 2 times 2 to get the cancel to get to the final equation that we need, KEQ is just squared then. Is that correct for the second one?
Right.
Okay, got it. Thanks.
Yeah. So for instance, if this equation, if I had this equation here as like 1/2 into 1/2, 1/2, and 1, in order for us to get this overall resulting equation down here, I would have had to multiply this whole equation by 2. I shouldn't put that there. I would have had to multiply this whole equation by 2, but I would have had to take my KEQ to the power of 2. And then I would have had to have this multiplied together in here. So enthalpies, they're easy. You just add them up and you just multiply whatever factor by your enthalpy. But for KEQs, you either have to raise them to the power, do an inverse relationship, take the square root, cube root, quadra root, whatever, and then the KEQs will be multiplied. So typically we're working with way bigger numbers here as well because of these rules. Other questions? Okay. So I wanted to ask a question that I skipped here. In this problem, which of is the original equation or the reverse equation more product favored? You can original or reverse. You can type in the chat. Is the original equation or the product or the inverse equation more product favored? Yeah. Yeah, the OG is more product favored. This KEQ is higher. So yeah, okay, great. If I told you your Q is equal to 1.5, which direction is the original equation going to proceed?
Forward.
Right. So remember the Q line, we have 0 to infinity for our Q. So if KEQ is at 4.72 here, and our Q is back here at 1.5, we're going to be proceeding forward to meet that KEQ. So what about the reverse reaction? Which direction is this proceeding? Yeah, so this one would be going to the reverse because our KEQ would be over here at 0.212. So this would be going in the reverse direction to meet our KEQ down here. Great. So it seems like that's a pretty comfortable concept for everybody. Perfect. All right. So here's an example that I would like for you to work. We have, oh, I don't remember what it's called. Copper sulfide, maybe? I don't know. Cu2S as a solid goes to T2Cu solid plus sulfur as a solid with a delta G standard of positive 86.2 kilojoules. And we have sulfur as a solid plus oxygen 2 as a gas that goes to sulfite gas with a delta G standard of negative 300.4 kilojoules. And I want you to I want you to find the delta G standard of the following. Cu2 sulfur solid plus oxygen gas goes to 2 copper solid plus sulfite gas. So find the delta G standard of this overall reaction. Yeah, that makes sense. Copper 1 sulfide, because you have to tell the charge of it. I never remember like how sulfur names change. But a lot of those metals like arsenic and mercury and stuff, chromium, you have to tell their state, like hexavalent chromium, copper 2, arsenic 3. Oh yeah, that could be it. SO4 2 minus is sulfate, right? SO3 minus is sulfite. SO2 is sulfur dioxide. Sulfur's not my thing. Not a big fan of sulfurs. So let me know when you get an answer, and remember that I'm never trying to trick you. Yeah. Yeah, great. Thank you, everybody. So yeah, this equation is very easy. All you have to do is add these two together. The sulfurs are going to cancel, and then you have your overall equation. And these delta G's are not KEQ. These are delta G's. Delta G's behave a lot more similarly to delta H, right? Gibbs free energy behaves a lot more similarly to enthalpy. All you have to do is add these together. So the delta G standard of this equation is negative 214.2 kilojoules. Is this reaction spontaneous or non-spontaneous?
Spontaneous.
Yeah. So this reaction is spontaneous. Is it endogonic or exogonic? Yeah, these mean the same thing, exogonic. So the reason that we do things like this is because this first reaction here is non-spontaneous. This reaction will not proceed by itself. So in order to get this reaction to proceed, we couple it with a spontaneous reaction. So we couple this first reaction with this second reaction to produce this overall chemical reaction, which is spontaneous. The delta G of this overall reaction is lower than this sulfur reaction here, but it's still spontaneous. It will still proceed. So a lot of times in chemistry, in labs, we need to couple different reactions together in order to get them to be spontaneous, in order to get them to be exogonic. So this is about coupling the reactions. All right. This is a reaction that you've probably seen a lot of times, and maybe you'll look at it in a new light, because essentially we have the combustion of sugar. So we have sugar C6H12O6 as a solid. Yeah, sorry, I'll come back to this in just a second. Here's the screen. Okay. So we have sugar, C6H12O6, and this can react with oxygen, gas, to produce carbon dioxide, gas, and water, which is exactly what like plants do. They have some sunlight coming in here and they have chlorophylls and stuff, but they're taking, well, they do it in the reverse. They take carbon dioxide, water, some photosynthesis, and they can create some sugars and oxygen. But this is essentially the combustion of sugar. We have to balance this equation. So this is 6O2, 6CO2, and 6H2O. But do you think that this equation is spontaneous or non-spontaneous, exogonic or endogonic, if you had to guess?
Exergonic?
Yes, so exogonic. Yep, so spontaneous, right? This reaction is spontaneous. Oh, I'm misspelling that bad. Spontaneous. I remember when I was an undergrad, I used to make fun of my professors for misspelling stuff on the board, and now I do it, and I am eating the karma that I have reaped on myself. So the delta G standard for this combustion of sugar equation is actually negative 288 joules, so 2,888 kilojoules. delta G standard. So this is a spontaneous reaction. It is exogonic. Yes. So typically combustion equations are very powerful, spontaneous, heat producing equations. Combustion is kind of like the poster child of what thermodynamics just loves. They happen typically pretty quickly. They produce a lot of energy. We use them in our world very frequently. And this is a naturally occurring process that happens a lot. So plants and, photosynthesis will use some of these similar type systems. Well, they kind of do it the other way, but a lot of how we consume food, we take sugars, we can digest it, we can oxidize it, and we can create some energy with the byproduct of carbon dioxide and water. So looking at this equation, describe how the KEQ will change with an increasing concentration. Describe how the KEQ will change with an increasing concentration, of, first we're gonna look at oxygen. So describe how the KEQ will change with an increasing concentration of oxygen. So type it in the chat. Increasing concentration. Yep, so type your thoughts in the chat. Yep, so other opinions? So if you, keeping in mind our KEQ equation for this will be CO2 to the 6th, H2O to the 6th, divided by O2 to the 6th, and then C6H12O6 to the 1. So if we increase this concentration here, we're going to decrease our overall KEQ because we're increasing a value in the denominator. So this will cause a decrease in KEQ. Does that make sense to everybody? Yes, so here our solids have a concentration of 1 and our liquids, but not our gases. For enthalpy, pure elemental have the values of 1, but for Gibbs free energy, they have the solids and pure liquids have a value of 1. Okay. So how about if we increase the concentration of water? How will this affect KEQ? So water here will have a value of 1. So there will be no change. Okay. Yeah, so solids and liquids have values of 1 in your KEQ equation here. Let me double check. I think it's just pure solids and liquids, or solids and then pure liquids, but let me double check this. Okay, so my household has confirmed that it's solids and then liquid water. It's not all liquids. So it might just be some liquids. Okay, so the rule for KEQ, you're going to equal 1 when you're a solid, when you're a pure liquid, so like water, and I might be updating to also when you're a pure gas based on information from my counterpart, which would mean this is wrong, but I'm still trying to double check that. And of course, my book has 0 helpful information about that. Okay, so looking at Google, it says solids and pure liquids are omitted. They have a value of 1. It doesn't say anything about pure gases. So I'm still trying to figure out pure gases. I thought pure gases still went by their partial pressure. I'm pretty sure they still do. I think it's just solids and pure liquids, which is what I first told you, but honestly, there's so many of these, like they're easy to get confused. So I can totally empathize. I think that pure gases, I think that this is correct, that I told you correct. Yes. Yeah, okay, so here's an example problem where they're looking at nitrogen gas and they have a value for nitrogen gas. So yeah, I think it's just solids and pure liquids, like I told you in the first place. Whew, confusing myself. Doruma.
Yeah, we have a Henry's constant for the pure gas.
Yeah, so you
Oh,
still have a
okay.
Henry's constant for pure gas. Yeah, pure gases still
Is
count.
K is the same.
Phew.
the same.
Okay, so we don't need to change anything. I had to double check myself, but great. Okay, so uh-oh. All right, so there's no change because our value will be equal to 1 since this is a pure liquid. Water is considered to be a pure liquid. So what about if we have a decreasing concentration? Decreasing concentration of sugar, C6H12O6. Okay, well now I'm kind of worried that I confused the crap out of you. Sugar is a solid. Yeah, so pure liquids and solids have a value of 1. So this also has a value of 1, so there should also be no change. So pure liquids and solids, pure liquids, the one you're going to see over and over, pure liquid, is going to be water. So pure liquid pretty much means water. And then solids have a value of 1. Yeah, I hope just practice. I hope I didn't confuse anybody. It's pure liquids and solids have a value of 1. So these are 1. All right. And then, so the last question, which of these values would you change to have the most impact? So which increase will have the largest impact on KEQ? Which increase or increases will have the largest impact on KEQ? Which increases will have the largest impact on KEQ? Okay, yeah. Yeah, Emma. So oxygen is raised to the 6th power. Carbon dioxide is also raised to the 6th power. So oxygen and CO2 will have the same impact if you're changing their concentration because they're the same. Yeah, I don't think there's any gas that equals 1. It's just solids and liquids. But it gets confusing because enthalpy has pure gases that drop out. So, but these will equal 1. So it doesn't really matter how you change those. But oxygen and carbon dioxide are both raised to the power of 6. And then last question, if you were to decrease the concentration of carbon dioxide, how would this impact your KEQ? So if you decreased your carbon dioxide concentration, how would this impact KEQ? Yeah, it would also decrease it, right? We're decreasing a value in the denominator and or whatever at the top. So it would decrease KEQ. Great. Okay. So we have this equation, C6H12O6 plus 6 oxygen gas, this is solid, will go to 6 CO2 gas plus 6 H2O, 6 H2O liquid, yeah. And then our delta G standard here was negative 2,880 kilojoules. So I would like you to find KEQ at standard temperature and pressure. Standard temperature and pressure, we're going to keep at 273 Kelvin. So 0 Celsius. So your R value is the same, 8.314 joules per mole Kelvin. So as a note, if your units aren't working out, this is kilojoules per mole of C6H12O6, but there's only 1 mole of this. So that's why I canceled out this mole, but this is technically kilojoules per mole. Yeah, Emma, I don't think that's right. Got 1. Okay, so to make sure everybody's at least on the right track, remember that KEQ is equal to E to the negative delta G standard over RT, right? Because we have our delta G standard is equal to RT ln of KEQ. So I'm asking you to find KEQ at standard temperature and pressure given this Gibbs free energy standard. Sorry, I'll put that back up. My calculator's not, it doesn't let me do this on the. Yeah, my calculator says overflow error too.
Yeah, it must be a large number because I'm getting an error.
Yeah. Okay. Zach, were you able to get it in your calculator and it spit out that value for you? And then how did you get around the overflow error?
Can you hear me?
Yeah, I can now.
Okay. What I did is, well, let's see if I did it right. I took the G, delta G, and then I times it by 10 to the third to put it into joules. And then I just divided that. I don't know, it just seemed to work. I did e to the 4.4 times 10 to the negative fourth.
Oh.
And so I don't know if there's a calculation error, but that's what I did.
Yeah, my number was like e to the 1268 because that negative becomes positive.
Yeah, that's what I originally had, and that's where I got the overflow from. So I wasn't sure if I was doing it right.
Okay.
There, and then you divide by 8.314 times 273. It was just a very large number.
So this gives me e to the positive. I got 1,273, which gives me an overflow error. Because you have to make sure to convert the kilojoules and joules, and then this turns positive. So this value up here is like 28,000. And then this value on the bottom is like 2,269.7, which gives you that large number. I'm sorry, this is higher. $2,888. It gives you 2,888,000. And then when you divide that by 2.269, you get like 1,269. But then when I put that, when I try to do that to the E, it doesn't like that. So my original delta G was negative 2,880 kilojoules per mole.
I get 3.55.
For your final answer. So e to the 1,269 is 3.55.
I put everything together in the calculator. That's what I got. Gotta use parentheses. The negative sign are canceled out. So
I originally got 3.56 when I didn't do the
that's what I have.
like to convert the kilojoules to joules.
I put it exactly as it is on the screen. I got 3.55.
So when you type this into your calculator, e to the 1,269, you got 3.55.
I had the whole thing together. I didn't do the 1.269. I have it as you have it up there. Negative 2.88 times 1,000 over, yeah.
Okay, so this is, so when I do the ln of 3.55, I get 1.26, which is off by a factor of 1,000. So that is close, but I think there might still be a conversion error. Okay. Okay, so we're gonna say that this is just an overflow error. Yeah, I took this from the book, like assuming that it was
I did it
solvable.
again. I get the same thing, 3.569.
Okay, well, I know for sure that's not right because
But you're not doing the conversion in the numerator. I just tried it with leaving it as 2,880 over the denominator, and I'm getting the number that you are.
Everything in joules instead of kilojoules.
You have to make sure to convert kilojoules to joules on top, or it's going to
Yeah.
give an error.
Yeah, when you multiply by 1,000, you have it in joule now. Everything is in joule. You have 8,314 down there as joule. That's the correct answer.
okay, maybe if we're changing units, so let's see, if we did e to the negative 2,888,000 kilojoules per mole, and then we
Tried it
converted
this
our
way already, too.
mass
If you do this, then you have to change the 8.314 to 0.008314, and you end up with the same thing. Like it gives you the same overflow.
Right. Okay. So then this problem, I got to choose another one for next year. You shouldn't get an overflow. Let's say that this is at what if we did 1,000 degrees Kelvin? Does that give us not an overflow?
I think I caught why he's getting an overflow. I put it in as 8,314 for the R value. And I got 3.55 when I did.
Okay, that would be converting the wrong way because we have 1 kilojoule would be 1,000 joules. So there's no way that this should be a bigger number. This should definitely be a smaller number. If you were converting this into kilojoules, it should be 0.008314. Okay, so if we change this problem to be at 1,000 degrees Kelvin, and we're going to make this our G for this, we're going to still say that that doesn't work. This problem. All right, canceling this for next year. And I got to pull this out of the book. Like, why would they do this in the book? But okay, so if we made this 1,000 and this magically stayed as standard, then we could get this value to be
I still get overflow with 1,000 Kelvin.
really? All right, I'm just gonna move on. I'll pick a one with a higher volume. I'm not getting overflow, but it's just giving me a crazy high number. So if this was 1,000 Kelvin, then this would become e to the positive 2,888 times 1,000 divided by 8,314, which gives me e to the positive 347. And then when I take the e of that, this gives me 7.23 times 10 to the 150.
So what happened to T on at the denominator? If you don't put, it's not RT, you put R.
So, okay, so in this equation, we have E to the negative Gibbs free energy standard divided by R times T. So R never changes. I changed my temperature from 273 Kelvin to 1000 Kelvin, which allowed me to increase this value to 8,314. And then that gave me a E to the 347, which is a really, really large value.
So R was 8.314 joules, not 8,314 joules.
Right, R is always 8.314 joules per mole Kelvin. I feel like this should be, I mean, maybe possibly memorized. Like 8.314 is joules per mole Kelvin. Like that is the R constant. Yeah. So this is 8.314. Maybe that's where the confusion is coming from.
Did your calculator give you that? Because when I do e to the 347, it still gives me overflow.
Yeah, mine gives me it.
I got overflow too.
I'm on my iPhone. I don't know. All right, well, this problem did not work the way that I wanted it to work. So I will come up with a better problem for us to look at on Monday that doesn't give us overflow. But the point of this problem is that you are using this equation, okay? And you're gonna plug in your Gibbs free energy, you're gonna plug in your R of 8.314 and your temperature in Kelvin. And then you have to take that to the E, and hopefully we don't get an overflow. So normally these problems work better. I pulled this one from the book, assuming that it would work well, and for some reason it doesn't. So I apologize about that. I'll look for a better problem that is testing the same thing. All right, so I don't think that I want to do the last problem because it's going to take more than 5 minutes. So I think I'm just gonna, with that beautiful last problem, I'm gonna conclude. So any questions about anything?
On Monday, are we going to go over the problem that we would have done today, or?
Yeah, I'm just moving it to Monday. Yeah. Other questions? Okay, so on Monday, I'll do the problem that I was going to do right now. I will find another problem that doesn't give us an overflow error when we try to do natural log calculations. But I guess for this problem, we should have gotten the problem that I was working on before, right? We should have, you should still have E to the positive 1,269. This can be your answer, right? That's your answer. So it's not wrong. It's just, this doesn't work in our calculators. Thank you for the well wishes for Friday. And I will see you on Monday. There's no class on Friday. So use the time to study for the final exam, use the time to work on other things in your classes, and we will have 2 final exam options, Friday, April 23rd, Saturday, May 1st. So have a good rest of your day. Sorry that this math is stupid, and I will see you all on Monday. Have a great weekend.
Bye. Have a good weekend.
Have a good one.
So Connor, I'm going to send you another link because I have 2 Zoom meetings. So I have to send you a link to my other Zoom account. So I will send that to you over email in like 5 minutes.
Okay, cool. Thank you.
Okay, yeah. Okay, Dan or Christian, do you have any questions? Okay, is that Uzi or Billy?